Good morning. So we were working on through this disinfection example. So we got to the point where we were looking at using the pilot plant dose to determine the T10 and T0. So we started with stating that the 2.5 milligram per liter dose was based on the experimental data that was provided to you. This T10 ratio is based on the client's desire for a basin with superior performance. The CT value of 40 was based on the analysis we did based on water quality and the requirements in terms of CT credit removal and the CT credit. So we could determine based on that, we needed 40 milligrams per liter a minute. We divide that by this initial dose, and that gave us a T10 of 16 minutes. So the hydraulic detention time is that T10 divided by 0.7, and that is 23 minutes. So then we'll use the equation for second order decay to determine the C in each of the cells, and that will allow us to then determine what the actual dose needs to be and what our detention time also is required. So I'm going to switch to an Excel spreadsheet, and we'll look here at this Excel spreadsheet. So I'm going to start here with going back to the 2.5 milligrams per liter. So that was the dose in the initial cell, so in cell 1. Now, cell 1 would have the diffuser in it, so that cell does not give us any credit. So notice there's nothing in this cell here for CT because we get no credit for any cell where there's a diffuser. We calculate the residual using the second order rate constant that was provided and the equation that I just gave you. So this is the constant dose in cell 1. We can then calculate, based on a hydraulic detention time, the residual leaving that cell. That is its concentration entering cell 2. We then do the same thing, and we continue through the cells. Now, notice here, with a hydraulic detention time of 2.3 minutes in each cell, gives us a T10, and that only gives us a CT of 30, which is insufficient. So now we can start looking at what do we need to do in order to ensure that that is 40. Well, we can increase the hydraulic detention time. So let's try 2.5. Well, that brings us up to 32. We can look at increasing the dose. Let's try 2.7. We're better, but we're not there yet. Let's try 2.9. Okay, that improves it. Now, you're playing off the dose, which ozone is generated using corona discharge. It's a electric, it's produced with high voltage. Voltage is about 15,000 volts across the dielectric. So you want to minimize the dose. So we're essentially playing off the contactor size, which is our capital cost, versus the operating costs. We can increase the hydraulic detention time further. And we're pretty close. So at a hydraulic retention time of 2.8 minutes in each cell and an initial dose of 2.9 milligrams per liter, we can achieve 40 milligrams per liter minute as our CT. So this here is the CT, and that meets the required value. So the CT, so the question is the CT is total for every cell? Let's just go back. So the CT is equal to the residual in the cell times T10 for that cell. So the residual times T10, and then I sum up that for the entire, each of the cells. I could add an 11th cell. Now, if I add an 11th cell, I can also look at reducing the hydraulic detention time, or I can look at reducing the dose. So, for instance, if I designed my reactor to have 11 cells instead of 10, I could reduce my dosage here to 2.8. And now the total detention time in the reactor would be 28.6 minutes. So I've just summed or multiplied the 11 times the 2.6 for each. So let's switch back. So we'll use the 2.9 milligrams per liter. We have a flow rate of 30,600 cubic meters per day. There are 1,000 liters per meter cubed and 10 to the minus 6 kilograms per milligram. And that is equal to 88.74 kilograms per day. Okay. So this information allows us to size the ozone generator. And the way ozone generators are purchased is actually on the mass of ozone that they can produce per day. This is the same information that we just looked at, okay? And we looked at this on Friday, but I just wanted to go through that Excel spreadsheet, and you can see here. And in this case, we have a hydraulic retention time of 2.8. So now we can look at sizing the reactor. So if we have a hydraulic retention time equal to 28 minutes, so we get 10 cells, each 2.8. That gives us a total hydraulic detention time of 28 minutes. So the volume of the reactor is just our detention time times Q. So it's 28 minutes times 30,600 cubic meters per day. And that is equal to 595 cubic meters. Now, so we've got the volume. Now, in order to size it, according to the textbook, the height to length ratio per cell should be equal to 4 to 1. So we'll let the height equal to 6 meters. And as I mentioned last week, here we want a very deep basin because we want to ensure that we have as much mass transfer of that ozone from the gas into the aqueous phase. So these tend to be very deep. So that would give us a length of H over 4, or 1.5 meters. So that's each cell. The volume is then equal to the height times the length per cell times the number of cells times the width. So our height is 6 meters. Our length per cell is 1.5 meters. We have 10 cells. And this is equal to 595 cubic meters. And that would give us a width equal to 6.6 meters. So the dimensions of the reactor is 6.6 meters wide by 6 meters deep by 15 meters in length. The last part that I asked you to calculate was the feed rate of sodium chloride and ammonia. And in this case, you're asked to determine a dichloramine dose of 1.6 milligrams per liter. So if we add ammonia and hypochlorous acid or sodium hypochlorite, what we would form first is the monochloramine. If we add additional hypochlorous acid or sodium hypochlorite, we form the dichloramine. So this is mono, and this is the di. So for every 1 mole of ammonia that we have present, we need 2 moles of hypochlorous acid or sodium hypochlorite. So we're just going to write this as ammonia plus 2 OCl, and that is going to result in the formation of dichloramine. And we want 1.6 milligrams per liter. So we need to convert the 1.6 milligrams per liter to a molar units, and we have 1.6 milligrams per liter, and that's our dichloramine. That has a molecular weight of 85.92 milligrams per millimole, and that is equal to 0.0186 millimoles per liter. So in terms of the dose of ammonia, we have 0.0186 millimoles per liter, and multiply that by the molecular weight of ammonia times the flow rate times 1,000 liters per meter cubed. So liters cancel, meters cubed cancel, millimoles cancel, and we'll convert to kilograms. So milligrams cancel, and that gives us 9.7 kilograms per day of ammonia. So that's how much ammonia we would need to add. Now, since the problem stated that we were adding sodium hypochlorite, not hypochlorous acid. We'll use the molecular weight for sodium hypochlorite. Remember, we needed 2 millimoles of sodium hypochlorite. We'll multiply by the molecular weight of sodium hypochlorite. And we do the same set of calculations. And we need 59.8 kilograms per day of sodium hypochlorite. So that gives us both the sodium hypochlorite dose that we need, and it gives us the ammonia dose we would need in order to achieve this 1 milligram per liter of dichloramine.